So the next thing that I wanted to do was go through the synchronization construct. So far we've seen the principles of OpenMP and the manner in which it works, and the parallel region, and the major ways in which we can distribute the work among threads. We've also looked at some of these, so a little bit of this I'll be able to do very quickly and somewhat repetitive. But of course, this is very, very important. So OpenMP, like other models of its kind, have to provide synchronization. Synchronization in the MPI context, of course, also exists, but it looks different. Obviously, when you send data, you need to know when it arrives and when it's available for use. The same thing happens here. You need to know when data is available for use, but you'll be using different means to do so. So there are actually, in the OpenMP world, there are two different reasons for synchronizing. One of them is to control the ordering of things. So in particular, if thread 1 is updating some values that thread 2 needs, thread 2 needs to be sure that they're available. So that kind of, there's an order. The other thing that we need to be able to do in this context is to, I guess you could say, avoid data corruption. To make sure that two things don't happen at the same time. And in that kind of synchronization, the ordering doesn't matter. So one of the examples we like to give for something like that is if you say that, that say there's a couple have a shared bank account, right? So the husband goes and deposits some money in the bank account, the wife goes and withdraws some money from the bank account. Or let's say perhaps they both depositing. It's an easier one to do. All right, that's better, right? So they're both depositing money. If they happen simultaneously, you could end up with a nasty situation where only one of those deposits is credited, right? So let's say there are two different ATMs, just happens to be exactly the same time. Each transaction retrieves the current amount, and let's say it's $2,000, right? So I think $2,000. He deposits 500. She deposits 700. His deposit comes up, but they both retrieved the same initial amount. She deposits the 700. He deposits the 500 right after that, and the 500 is the only one that makes it, right? So there's 2,000. You just lost $700. That's not a good idea, and could lead to a lot of trouble that evening too. So, so you want to avoid it. So sometimes the ordering just does not matter, and for that we have something that we call mutual exclusion, and its job is to make sure that two threads are not accessing the same code or accessing the same data at the same time. And there are several different ways in which some of these things can be spelled in OpenMP, and sometimes they offer the same, more or less the same functionality with slightly different, sometimes slightly different implications in terms of behavior. We've seen barriers. So as I mentioned at the start, and we're not going to say too much about it here, you as a programmer are responsible for the correctness of your program. So if you have different threads updating data and using it, you have to make sure that data that you need to use is available. It's your problem. All right, so if you have two loops like this one, where one of them is creating values for A, the next one's using it, you're going to need to insert some synchronization to make sure that that happens. And the obvious thing to do here is to put a barrier, so when you parallelize each of those, then the first loop completes execution, the barrier, and then the second one continues it. There are a few situations, or there is, I guess, a situation where you don't need to do that, and that is if you know. So don't guess, but you know that the loop iterations are going to be mapped out identically. All right, then you can actually suppress that. So you, in fact, so if thread 0 has, I'd say, the first 100 iterations in both of the loops, then actually in that case you don't need a wait. All right, so the values will be available. That is only guaranteed if you have a static schedule and certain other conditions apply. So in particular, you have to have the same set of loop iterations. In all other cases, you don't know. All right, so slightly risky to assume it, to make sure that what you're doing is right. Of course, barriers are expensive, right? So we have, as you probably, if you've been listening this morning or if you've used OpenMP before, you'll know that there are a lot of implied barriers in OpenMP, and that means there's potentially a fair amount of time lost waiting if threads are not proceeding at the same pace. However, it's still the most fundamental and the most important synchronization in OpenMP in terms of its availability. And as I said before, you can use it explicitly if you need it. So if it's not implied by a construct, you can actually insert a barrier. There is a construct to do that. So it's implied, both implied, so we have implicit barriers at the end, for example, of work sharing directives. Anything else that do you remember what else it was? The end of a parallel region, for example. All right, and there are also some also explicit barriers. So we have an explicit barrier here. The OpenMP 4 would have a barrier, but we've suppressed it. We put in that no wait to say we do not want to stop there, want to continue. However, there will be a barrier at the end of the parallel region, and that one we can't suppress. There will always be a barrier at the end of the parallel region, so the threads all sync up at that point. Okay, and again, we've seen that. For mutual exclusion, this is the case where we want to be sure that threads are not doing the same thing or not accessing the same data at the same time, but we don't care about the order. There are a couple of different ways in which we can do that. And the main thing to consider when you're trying to use them is that if you have a big region, so we call these critical regions. So if we mark a block of code as being a critical region, that means that while one thread is executing that critical region, the others cannot do that and are potentially waiting. If there's a lot of code in that critical region, we could be slowing down the performance by quite a bit. And I have seen some real-world codes where this mistake was made. In other words, people had packed a lot of computation into a critical region and then wondered why they weren't getting good performance. It's possible to do that, even if we're perhaps not thinking so much about the implications. So others may have to do a bunch of waiting. All right, so how do you do this in OpenMP? So the main construct, if you like, most one is simply called critical. When I put critical on in this clause here, it's saying that only one thread at a time can execute this procedure called consume. If one thread is executing that and another thread reaches that point, it's going to wait. Okay. So, so again, you really would like there to be not too much work inside that. You don't want to don't over protect your code. Okay, atomic. I heard somebody saying something about atomic before, so you might already know this feature quite well. Atomic is if you think it's a very lightweight kind of a critical region, if you can use that term. It's really protecting updates to memory locations. So we can express atomic operations in OpenMP. So it's just a very typical simple update. So usually a summation of some kind or a subtraction of variables. I think I'll jump across that right now, but the latest spec can actually allow you to say that it's an atomic read or write as well as being an update. Ordered is something that most of us would seldom use because it actually requires or introduces some sequentialism into a parallel region. So if for some reason you decide you want to execute a piece of code inside a parallel region in sequential order, you can use the ordered construct. And that applies to parallel loops. And if you want to use it, as you see here, you have to say so when you're introducing the loop. So there's this ordered clause. So I've got OMP4 with ordered. It says inside this loop there's going to be an ordered piece. And which the ordered piece, that piece of code is going to be executed in sequential order. So most of us say, well, I don't think you need to use it, but if for any reason you want to test something, see what happens, you could consider it. But most of us ignore this, I think. It's fair enough to say. Okay, so that was a real rush through synchronization. So we have barriers, which are implied in quite a few constructs. If we need a barrier, there's also a barrier directive, so you can insert them if you need them. You have to think about whether you really need them because there is clear waiting implied. So if you don't need it, use a no wait clause. Okay, so know where they actually implied so you can make that decision. And if you want to be sure that two different threads are not accessing, not updating some piece of data simultaneously, the very light way to do something, if it's really just one memory operation, is use atomic. If it's a little bit more complex, you'll need to use a critical directive. And again, don't put too much code in there, because the more code you have in there, the more likely that others are going to have to wait, and possibly for a long time. So don't over-constrain. Let's just do that. OK, so there's just one more thing I wanted to say before we totally sort of leave this area. And it's sort of like, you know, everything's, so OpenMP's pretty simple, I think, once you understand the concepts. It's easy to say that if you've been using it for a while, but I think it's fairly straightforward. However, like everything else, there is a little bit of dirty linen in the bottom of the basket. And so the problem that we have with OpenMP, and I know that you'll know this, but you may or may not have thought very hard about it, is that actually, even though we say that all the threads can access the shared data, our hardware just doesn't really quite match that at all. So we have, this is obviously a little bit stylized, but if we have this shared memory out there that all the threads are very happily reading and writing to and getting data and using it to share, actually most modern systems have cache, right? And it's obviously a little more complex in this picture, but this will serve our purposes. So what happens? Well, actually, what's really going on is that when threads are accessing data, they're going to be copying blocks of data into their local cache. And guess what? Cache is probably not shared. All right? So it might be shared by a few threads, so there could be something a little more complex. But for the sake of argument here, we'll assume that each thread has its own cache. So cache isn't actually shared. All right? So what happens? Well, the first thing that happens, and that is allowed to happen in the OpenMP context, is that values might temporarily be different. So you may have some, I'm talking about shared data here. So the values of shared data might be slightly inconsistent. We expect the system itself to actually help out here. So we'll talk about that in a moment. The other thing that can happen, so you may have data in cache. Let me just say that again. So you may have data in your cache, and let's say that a thread running here has updated this element A. All right? So A is actually in shared memory, and other threads may want to see that value. What we have to do here is think about, well, when are the other threads going to see that value? Okay? And this may be a little system dependent. Okay. So that thread's updated it. Its update is in its local cache. That has to propagate back to main memory so that other threads can see it. And there's actually another step that has to happen. The other threads have to retrieve it from main memory. Okay? So there's a little bit of work going on there, right? So, so OpenMP is hiding this from you for the most part. The other thing that can obviously happen while code is working is that it will have, and anybody who's a computer scientist here will know this, it will be holding some data in registers. And when a value is in a register somewhere, guess what? That may or may not, depending again on the architecture, may or may not be back in shared memory. Probably isn't right now. Okay? So thread 1 has updated that value of A, but it's in a register somewhere. But it's supposed to be shared data, so the other threads need to be able to see it. Get the point? All right. So the system has to make that happen. And what happens here, there are kind of two operations that have to happen. So threads have to do what we call flushing. They have to flush their data back to memory. So I have data that's in their registers in their own local cache. It has to get flushed back to main memory. And threads actually have to also do a flush to retrieve the latest values of data. Right? So it's sort of like a bit of handshaking with memory, right? And so we call that flushing. The good news is that most of the time this happens automatically in OpenMP. So there are a lot of different constructs where, as part of the construct, the threads will write the shared data back to memory, and will make sure that they've got the latest values. So most of the time this is invisible. Okay? But we do have to know that happens. There is also something called a flush construct, which is one of the trickiest pieces of OpenMP. And so I don't want to say too much about it here, but I also don't want to completely hide this from you, because because you do need to know it exists. And its job is actually to do this kind of handshaking with memory. So it's not a synchronization between threads, it's a synchronization between threads and memory. And it basically tells a thread to write back data or to look for global data. Yes?
So is that only for data that is supposedly used by another thread, or is it for any piece of data?
You could flash any shared data on it, but if you were doing that specifically, you would have to have a reason for it.
No, but what I'm saying, what it does automatically, is it done? Does it make a conscious, proper decision based on how the data is used, or is it like, okay, I have a variable and I assume it might be used, so I'm just going to flush it?
Good question. So let me see. Maybe I'll skip the other things here. So I have a list, and I'll probably, in fact, just pretty much jump the slide doing that. But there are a whole bunch of constructs where this is part of the construct, so you don't have to worry about it. From the point of view of the programmer, just assume that all shared data is made consistent. This is the right way to say it. All right, so I kind of would like to go through this quickly because most of the time you don't need to really know about it, but on the other hand, it is part of the features and I don't want to completely hide it either. So most of the time, for example, at the end of a work sharing region and that barrier, everything will be flushed. That means that the threads write back any data that hasn't been written back to memory will be written back, and it will also check for updates. So everything is made totally consistent. Okay, is that answering it? Okay. So usually you don't want to do this yourself, but I'm going to give you an example. In fact, I think I might just skip to the example. And you can have a look at those at your peril, all right, if you want to. But you can do this specifically if you're trying to do some sort of low-level synchronization, which is why it's here. Let's see if I can remember this one. Okay, so here we have each thread. So we've got a parallel region. We've got a shared variable called isync, which okay, actually is an array, so that's a slight typo here. Okay, so we've got this IM, which is the thread number. So it's getting a thread number. And we're setting the local value of isync, so isync, my own one, to 0. And there's a barrier, so everybody's done that. So they've all initialized their own copy of this isync to 0. They're doing a whole bunch of work, and when a thread is done with its work, so it's called to this routine work, it's setting its value, so it's like a flag here, right, to 1. Just basically just signaling I've done this. And then it's doing the flush. What that flush actually does then is write back that isync value to main memory. Doesn't do anything else at all. It's not a barrier of any kind. It's making sure that that value is written back to memory. Okay, and this is assuming this is obviously a code fragment with things missing, so it's not intended to be executable code, but there's some concept of a neighbor here, and in this case, the loop is not going to, or the work is not going to continue until the neighbor has actually done its work. So what's it doing here? It's actually, this one flush doesn't do that for you. This flush is writing that back to memory, but it's not going to ensure that you've got any new values of other data. So this one is actually going to go through a little loop here, which is testing the value of the neighbor's isync. Has that been written back to memory? I mean, is it one and written back to memory? So there's a little bit of handshaking going on here. So if you really want to, and I'm not recommending this, but if you really want to do this kind of low-level synchronization, you can. All right, so the first flush is writing its value, this isync value, back to memory. And the second one is also looking for, are there any updates to isync? And in particular, is the value of my neighbor at 1 now? Okay? Yeah.
In this, when you are doing the flush isync,
yeah.
Is the thread only syncing the part of isync that he manipulated, or is it trying to sync the whole array of isync?
It would probably, I think, sync back anything that it has in its local data. So, so this is writing back any updates to it. So think of it as updating the value that it's changed.
But and that does not imply that only this thread will do it. Other threads won't.
Yes. Okay.
Other threads will
yeah.
also do
You can see why this is the hardest part. This one is, the thread that encounters that is going to do that operation. So this one is only the thread that's doing it is doing that. It's got nothing to do with any other threads at all. You get that? Right. So when a thread hits that flush operation, it's going to write back its changes to async to main memory. That's all that will happen. Okay. If there are updates there, it will also. It's actually specifically on this async variable. Yep. Okay.
Do you know if you can find the parameter how many times OpenMP does the flush without you knowing as well? Because that's quite important.
Yes, it is. And that's to some extent, I kind of, maybe I should have skipped this because I really like to move on a little bit. It's very hard to, yeah. So here's when it's guaranteed to happen. And on some systems, it will happen a lot. And in fact, if you're doing a lot of changes, the first thing is that mostly it happens anyway. So that's just because of the memory consistency. And in fact, one of the biggest performance problems is if you're changing things. This is what Deepak was referring to before, is if you have two different threads updating things that are on the same cache line and they invalidate each other, they're going to be doing a lot of reading and writing behind the scenes. And that can seriously degrade your performance. It's the single biggest problem. All right. So yes, a lot of this is going on anyway, and there's one way that you can sort of explicitly do this, and we don't really encourage it, which is probably why I've spent too much time on it already. But in particular, yeah, I'm sorry about that. There's no easy way to explain it, and it sort of always messes things up a bit. And you probably don't want to use it. But anyway, the main thing for you to know is that most of the time, actually, you don't have to think too much about how things are written back. Because it's guaranteed to happen on barriers, when you leave work sharing regions, on locks, and also when tasks are scheduled, which I'm hoping we can still get to despite me messing up this bit a little bit. Okay, so there are certain points where you can be sure that this consistency is achieved, and most systems will actually possibly even overdo things to maintain consistency, right? And sometimes at a bit of a cost. Okay, so I wanted to come back to the memory model very briefly and just mention a few other things that we can say here. So firstly, if you remember that there's shared memory and there's private memory. Using private memory is sometimes a good idea for performance, and obviously sometimes it's needed for correctness if the threads have to have their own values. So it has both aspects to it. And there are some defaults in this thing, and I'll say those pretty quickly. So static variables, global variables, common blocks, if you use them, if you're a Fortran user, are by default shared. Again, just to jump to the bottom line, there's a default, right? So in other words, you can set the default, and normally that's shared for almost all of the data. There are some very specific things that aren't shared, but you can change that. And especially if you're trying to debug a program, one of the things that is encouraged is to say default none, so that you're actually forced to say whether something's shared or private, and that makes sure that you've actually really looked at all the variables and made that decision, are they really shared or not. So there are a few things that are private. One of them is the iteration variable on a parallel loop. So each thread has to have its own chunk of iteration, so that actually has to be private. If you're calling, actually I'll talk about this one in an example at some point. I'll skip that here. Okay, so most of the time data is shared unless we say something specific. It's the bottom line. Okay. One of the things that I think I'll just show this in examples too in order to move on, but private variables are sort of by their definition undefined when you enter a parallel region and undefined when you exit it. So right. So it's there. These variables actually inherit their type from a variable of the same name and the calling procedure, but they're not the same. So I'm going to just skip these just to catch up a little bit on time. Okay, so totally trivial example, and in fact, completely meaningless piece of code. So we've got this is equals 0 outside the parallel region. We've got this parallel loop with is being private. So IS will have the same type as the variable called IS in the outside of the region, but it is a separate variable. So, so this code is actually incorrect because this IS inside the loop wasn't initialized, right? So even though IS is 0 outside the loop, that's a different variable, has different storage location. So this is actually not correct code. Just a very quick comment. There are a few programming models that have different ideas about this, but you are not supposed to be able to access the private data through tricks either. So you're not supposed to, or not allowed to, is the right word, to use a pointer to try and access another thread's private data. Don't do it. Okay. Okay. So what if you did want to initialize something, and what if that IS equals 0 was intended to initialize all of those private copies? Well, that's a pretty common thing to want to do, so it has to be allowed. And to do that, we have something called Firstprivate. And I'll show these in a moment. So here, very simple, with the parallel do, and instead of saying private IS, we say Firstprivate IS, which means it's both private, but it's also initialized by the value of the variable with the same name. Sorry about that lengthy thing, but that's what it is, from before the parallel region. So each thread, including the master thread, has its own copy of IS inside the parallel region, and they're all initialized to 0. Okay? So we got it right. If we were trying to print out something that was a result of that parallel region at the bottom, we still don't have that, though, because this IS after the end of the parallel region is still not associated in any way with the IS or the different copies of IS inside the parallel region. There is, and again, this is complete nonsense code here, so don't try to get any particular meaning from this one. However, there is another way in which you can do that, and that's another clause that's called last private. So last private means that after the parallel region has ended, the variable in the master thread with the same name, so that the thread that continues at the end, will have the value that this would have in the last sequential execution. So here it would be the value that was obtained when j equals 1,000. So it'd be the very last value. There's potentially a little bit of a performance hit in using last private because it might have to figure out what the last iteration was or what the last value was. But if you want to have that value transported back to the enclosing environment, you can do it. Okay, so first private and last private, and each one of those implies private. And by the way, otherwise, and I guess this is one of those things where you'd say the rules are just common sense, you're not supposed to have more than one of these data clauses for any variable. So you don't want to say, obviously, that something IS is shared as well as private in the same context, right? This is the only exception to that, is you can say something is first private and last private as well. Otherwise, you can't do that. Okay, so just a little bit more power to the private. Okay, this is actually completely trivial, but it's always good to make sure we know what we're doing. So if we have just some variables here, defined outside the parallel region, so just call them A, B, and C because I'm not very imaginative on these things. And we've got a parallel region, and for that region, B has been declared as private, C is first private, and their values outside the parallel region are 1. So what's shared and what's private here? Well, what's shared? A, all right? Okay, so A is shared, B and C are both private, so first private implies private. Which ones are defined at the start of the parallel region? A and C, right? So B is not, because B, remember, it's a whole new variable with the same name and the same kind. Okay, so A and C are private, and at the end of the parallel region, A will have whatever value it received in the parallel region, which may or may not still be 1. So if it's shared data, right, so it will continue. And B and C, the values outside the parallel region are not going to be related in any way to what happened inside the parallel region. We don't have a last private there. Okay? So pretty simple, I think, and just a few shortcuts, I would say, for some common things. Sorry, yes?
So what happens when we say C is the last private, and each thread may assign different value of C?
Oh, okay, that's the whole problem with last private, or it's not a problem, but potentially a performance problem, is that that in fact only one value can be transported to the outer environment, and that's the one that you would have if you were executing it sequentially. The last iteration, the value from that last iteration is the one that would be transferred back to the outer environment. Okay, yeah, and that's why it has potentially a little bit of cost associated with it. Yeah.
In general, with OpenMP, do you put these pragmas and such before the loop body? Do you ever have to put these things in like a loop body?
You have to put these ones actually when you're calling it. So these ones are mostly either associated with the parallel region or with the loop, right? So you put them at the start of the loop. So yeah, so you wouldn't do that inside the loop, or it wouldn't, right?
Is that pretty unusual to have anything where you need to put things in the loop?
Let me try and show you an example. There's this one piece I didn't talk about before, and it might clarify things. But you can't, if when you're entering this region, you need to know, are they shared or private, right? The implementation needs to know that. So you can't suddenly change that or decide that later on. So you need to say that first, at the start of the parallel loop or the start of the parallel region. So you have both options. Okay, reduction we've already seen, so just a reminder that that's something else that we can do. Reduction, of course, is in a sense sequential because you're summing or multiplying something or looking for a minimum, but they're so very, very common that we always try to provide some easy way to specify that, and OpenMP is no different. One of the reasons that we have this is in an example like this one, a compiler probably could find that pretty quickly. So, in a way, you'd say, why do I have to say that? But of course, the reduction might be in some code that's further inside somewhere. So we like to or require you to actually say that there is a reduction coming. One comment about reductions. Doing a good job on reductions is actually quite a lot of work, and very early implementations sometimes did a really bad job on it. So it's one of the places where you can sort of test the quality of an implementation too, is by seeing how well the reduction is handled. There are a lot of different optimization possibilities associated with that. Okay, so it's in a kind of accumulation, and since this has already been talked about, the implementation then does exactly what you would do manually in some form or another. It's going to create local copies and have the threads do their local sums, and there will be some kind of accumulation happening, and it's invisible to the user. So that's the good part about it. The other thing to note, though, is that you're not going to be able to access the result until the next synchronization point. So usually that means leaving that construct, and outside the construct, you'll be able to actually access the sum, right? But not beforehand. Another comment is, so these are sort of the most, I hope the most common things. So you can take a maximum or a minimum, and addition and multiplication. There is no guarantee, by the way, that if you have a reduction and you've used the reduction clause, and perhaps you do that a couple of times in your code, there's no guarantee that you will always get the same order of evaluation, right? So if you run the same program with using the reduction clause and you run your program 5 times, the order in which the updates are performed could differ from run to run, so that could lead to some subtle different or small differences in the results, and that's just the way it is. So the implementations are not required to do the same thing every time. Okay. Which of course is one of the challenges. Okay, so default clause, I think we'll skip that. Just say it's a good idea to use default none while you're developing code, but it can be a pain in the butt in other ways, because then you may have to do a lot of what we call scoping, so data scoping. So if you have to spell it out for every single variable, then that's work. So quick question, actually, I think this one's really, really obvious. So looking at the defaults. We've got just 3 variables here, unless I messed up. So in one case, shared as a default, so with 2 variables declared to be private. In the other case, we've made default private, and we have to say that something's shared. And yes, they're the same. Okay, so there's one other point I wanted to make, and I'll just do this here, just a very, very short one. So one of the things you can do if you have a lot of data is actually do something that we like to call outlining, and that's create a function that contains a lot of the work and a lot of the data. And this is the point that I actually did want to come back and make. So when you, let me just check and see whether, yeah, I think I'll just use this one. Okay, so when we create a parallel loop here, what we've got to do is worry about whether which data is shared and which is private, all right? If we have default none, we've got to spell that out. If we go for a default, we may have a lot of work still to do to say whether things are shared and private. One of the things that I didn't talk about before, sort of glossed over, was what happens when you're making a procedure call inside here. So variables that are automatic or are local to a procedure inside here are private. Okay, so in other words here, these things that the variables that we're declaring inside this procedure that we've created are private by design. We don't have to say anything about them. So one way to avoid doing lots of explicit scoping is to create a procedure of your own, put all the variables in there, and then you don't have to say anything. All right, so they are private. Each thread has their own copy of those when they call them. Okay, so this is what I was referring to when I had the question before about what else you can say, because other variables that you're accessing right from the start, you have to say, when you start the directive, you have to say whether they're shared or private. This way we can get away with declaring lots and lots of things to be private if that's the case by packing it into a procedure, and then we don't have to say anything at all. Okay? Okay, so I try to say very little about thread private, I think, just again in the interest of time, but it is actually important if you need it. So there is another kind of data. So we've had shared data and private data, and we've seen that you can have first private and last private, and we have this kind of special case where we have reduction variables that are going to be used to accumulate values or determine a maximum or minimum. Thread private data is most easily, for me at least, understood in the Fortran context where, and how many Fortran programmers we have here, where you may have large amounts of data packed up into common blocks. And the question is, if you have a common block with a bunch of data and you want to share it, that's fine, that's your default. But what if you actually would really like each thread to have its own copy of that common block? And it gets more interesting than that. You can say, well, okay, I can create private data there too. We can do that. But what happens if you have a program where you actually enter a parallel region, you do some work on all that huge amount of data, and when you use them, it tends to be a lot of the data in the code. And then, for whatever reason, you're leaving the parallel region, doing something else maybe, and starting up a parallel region again later on. But you really wanted to have the same data. You don't want to lose those results in the interim. And you don't want to have to copy it all somewhere at the end of the parallel region. You want it to just be there. In other words, you want it to be persistent. Okay? So thread private is the OpenMP solution, if you'd use that word, to providing persistent data. Which is data that's private to a thread, but you can leave the parallel region, and when you start up a next parallel region, you got the values that were created there in the previous parallel region. It's persistent data. Okay? And there are some rules on when you can use that, and that's because that doesn't always make sense. So in particular, if you started up a program and you had, 64 threads, each thread had its own thread private data, created some values there, you leave the parallel region, then you start up a new parallel region, and this time you have 128 threads, you have a bit of a problem, right? 64 of those threads don't have any thread private data. So one of the rules on this is you have to have the same number of threads across the parallel region. So if you want to use this, that's why I put here, consult the specification, so have a look and make sure that the rules apply. That's the main one, is that you don't change the number of threads. But anyway, so there is a way to have persistent data. It's still not shared data, this is keeping it internal, and it's called thread private. There's also a way to initialize it, so you can copy in data, at the start of the parallel region. So the master thread can initialize everything from its copy. Happens logically after the threads have been created, but before they start the work, so that the data is actually initialized. And again, this is Fortran because it's the most common context of doing it. And you can actually create a thread private common block, so the entire common block is thread private, or you can actually take fields from a common block and use them and initialize them separately. Okay, there is also a means of broadcasting data, which is from one member of a team to the rest of the team. So again, if you want to use these things, I suggest you read up and have a look at them later on. But you can use, this one's called copy private, and this is being used here with a single clause. So this what's happening is that the thread that executes this is going to broadcast. This is a real broadcast in this case. It's values of these variables to all the other threads, and that makes them consistent as well. So there are a few other things that you can do. Okay. So there's quite a few different clauses, but the most important ones are shared and private, and they get you almost everything. Right? So everything else is sort of small optimizations, I think you could say, or small extra help in some common situations. All right, so there are two things that I would still like to do in the remaining time, which is why I've been pushing it a little bit to make sure I get to them. And one of them is say a little bit more about the runtime library and the things that we can set, and the other one is to talk about tasks. And I was particularly concerned that we don't run out of time to make sure that we say something about tasks before I wrap up. So I think we'll do it. Okay, so right at the start, or say not right at the start, but partway through the morning session, you wrote a small version of Pi where you're using runtime routines. So we had a parallel region and otherwise used runtime routines to actually, if you like, implement the parallelism, to get the threads to do some of the work and share in it. So you could write entire programs that way if you want to, right? So explicitly using the thread IDs, accessing those, and using the number of threads to make decisions on how the work is to be mapped out among the different threads, and getting them to coordinate their work. So that actually, they're simple but quite powerful. And it's pretty common in particular to retrieve a thread ID to find out what's going on. So it's a common requirement. But there's more to the runtime library than that, all right? So those are very basic ones, very widely used, but there are some other things that we can do in the runtime. And it's sort of, they're kind of two basic things that we want to do. One of them is to get information from the environment. Who am I? All right, that's the obvious one. How many threads are there in my team? What is the value of? All right, is nested parallelism enabled, for example? Right, so other things. What are the settings? And the other one, of course, is to change something. So either to override a default, or to change the setting that you changed beforehand, or to change a setting that perhaps you created in an environment variable. So change something, query something, change something, get information. Okay, and as you've seen before, you need a header to actually use them. Okay, so most common ones. All right, so setting the number of threads. All right, I want 4 threads. You can do that in a number of different ways. You can set the number of threads as a clause, right? So you can OMP parallel and then number of threads as a clause, num threads. But you can also use a library function to set the number of threads. If you do that, you're not setting the number of threads in the parallel region that you may be in, right? If you're in a parallel region, that parallel region already has its team of threads. You're not allowed to change it. You will be setting it for subsequent parallel regions, okay? Very important. When you're in the parallel region, you have your team of threads. You don't monkey around with those team of threads while you're still in the region. You can only do this for later. Okay, so you can set the number of threads that you want the next parallel region to use. Getting the number of threads, you've used that already to make sure that you know what you've got. If you're going to divvy up the work, you need to be sure. And remember that it's possible, so Deepak already said this, it's possible that you get fewer threads than you asked for whatever reason. So it's always a good idea to check, even if you think you know what you have, make sure that you're right. Okay, get your thread number, get the maximum number of threads that are permissible. Are you in a parallel region? All right, so remember that because we have this notion of orphaning, we have procedures that don't have a parallel region in them, but they will have some constructs. It might sometimes be executed in parallel, it might sometimes be executed serially, you don't know, so it's good to be able to check. All right, and you can also check, there are a few ways in which you can check your environment to find out what is available to your program. So here's one, how many processors are there available? Okay, the threads one is very important, of course, because sometimes we really want to be sure we get what we want. So, you know, especially if you've been experimenting with things and you think you know exactly what thread count is going to make sense for your program, you want to be sure you can do it. And you want to also be sure that the system doesn't do something else, or you want to do your very best to make sure you get what you want. So one thing that you can do to influence the numbers of threads that are executing is, so well, depends a little bit on the defaults here, but if dynamic threading is potentially enabled, right? So on a general purpose computing system, so not HPC, in a non-HPC environment, so OpenMP is not just for HPC, right? Then it is quite possible that the system will, by default, reserve or want to reserve its right to adjust the threads to suit the resources, okay? Which means that the default could be that it can dynamically change the numbers of threads. If you don't want to do that, say so, all right? So do the setting, so set dynamic to 0. That's an example of saying I'm going to change or make sure that, you know, you may or may not be overriding what was there, but I want to be sure that the system does not giving itself the right to go and change the number of threads. Okay, so set it explicitly. All right, set the number of threads. This one is saying I want to go for the maximum that you have. I'd like one for each processor that's available to me, but of course you might have 16 there or 64. So set the number of threads you want, and inside here, doing again, this is just like our previous SBMD code, we're getting the thread number, and also checking to see what thread number we actually got, and making sure. All right, so requesting as many as you can get here, basically, and also, I forgot to say this before, but also you really only want one thread to be doing this. So there's a small chance of corruption if there's more, so want to play it safe, just have one thread doing that update. Only one needs to anyway, right? Oh, and by the way, it's flushed at the end of single. All right, so since we bothered saying that. Okay, so there's always a chance that you get fewer threads for whatever reason. Something has become unavailable, so it's good programming practice to always check, even so. Okay? All right, so runtime library routines help you try and set things to to query the environment. What resources have I got? What do I need? And also to try and establish your requirements. Okay, so they're all pretty simple, I think, but powerful and can be quite important. Okay, so setting threads, figuring out what your resources are. Is it dynamic? Notice in these two cases, implementations don't have to provide these. I would assume that they all provide dynamic. I don't know if anybody has nothing with nested. No, I think I don't know. And a few years ago, there were definitely implementations that did no nesting. So it's something that's definitely worth checking. Okay. Okay, so most of those I think we've already seen. They're sort of basic runtime functions. There are a few others, and I'll go through these. First of all, the schedule. If you remember, the schedule was how gave you, or allows us to give the strategy for parceling out the loop iterations to threads, right? So, well, what if you're not sure? Okay, if you're not sure what you want to use, or if you think something might change, you could actually make that decision, defer that decision to runtime. So you can have a runtime schedule, and if you set the schedule to runtime, that means that you can also use routines to actually set it. So there may be times where, for example, you want that to depend on something that you're computing. Okay, So you can set the schedule or retrieve the schedule that's actually will be used unless you do something else by using these runtime routines. The other thing that's, I think, interesting or important in the runtime context is nested parallelism. So as I said before, it was actually, although it's potentially, I think, a very interesting feature in terms of being able to cope with different amounts of parallelism and perhaps even different levels of parallelism inside your computation, so it can be quite natural in some cases. It had a rather sorry existence for a long time in the sense that it was often not implemented, and it didn't have a lot of support in the actual language itself. So you could create parallel regions and do some things with them, but the expressivity was a little bit limited. So there's been quite a lot of change to the runtime library to make it a little easier to actually use parallel regions and to figure out what's going on inside them. So first of all, there's a way of setting, or at least, again, if your implementation doesn't provide something, this won't help you, but you can override defaults even dynamically or outside, in fact, by setting something to be nested. So set nested will say, I want to activate nested parallelism. And you can also set the numbers of threads. So I'm mixing up things here a little bit. I'm going to kind of say a little bit about the environment variables in a moment. But you can also set the number of threads that you want to execute different levels independently of each other. Very important. So in other words, if you have in the parallel region, the first level parallel region, if the team has 8 threads and each of those threads creates its own parallel region inside, they don't have to also have 8 threads as well. They could have a different number. Could be more, could be less. So, so there's more power in the sense of enabling these things to have their own defaults, and that's important. Okay, you can actually set or retrieve the current value of the number of levels that are active. So active means, literally it actually means that there are levels where there's more than one thread executing them. So if you say that, that you want to have at most 5 levels of parallelism inside your code, you can set that. There will also be a default. There's also going to be some kind of a default in terms of the overall number of threads that you can use. So, okay. All right, so one of the problems originally with nested parallelism, even where it was available, was the fact that when you created one, so we've got the master thread creating a team of 3 threads. So there'll be, actually this is rather badly done because the blue one in the middle is thread 0. So it's 0, 1, and 2. And each of those created a new parallel region. So in each of those parallel regions, you've also got, guess what? It's got its own master, thread ID 0, and then thread ID 1 and 2. If your program in some way wants to distinguish these threads, it can't do it. Or at least it couldn't do it, right? What would you have here while these are executing are a whole bunch of different threads, all with ID 0, some others with thread ID 1, and others with thread ID 2. And there was no way whatsoever in which, at least if you were, let's say, printing data out, you could tell which one had been doing something. So there's actually a bunch of library routines added now so that you can actually figure out not just who am I, so you get your thread ID hasn't changed, but you can figure out which level you're in by retrieving the level of parallelism that you're at and figuring out which your ancestor threads are. So if you need to be able to distinguish things, that's really important. If you don't need that at all, of course, then this is probably irrelevant. But it turned out that there were plenty of situations where that extra ability was quite important. Yes?
Is there any particular reason why the thread numbering is not consistent in the sense that when there's third level parallelization, why not give a unique thread number to every thread? Okay.
I guess that would have been a possible way to go, but it would have caused a lot of grief in other ways in terms of language. So when we talk about constructs and discuss how things are allocated to threads, we're sort of assuming this consecutive numbering starting with 0, and master thread always has 0. So if you think about it here, just going back to this one, in this team over here, this is the master thread, right? And we're checking to see whether it's the master thread by looking for the ID of 0. If it suddenly wasn't 0 but something else, which could be perhaps a list of parameters, it would have made a lot of things a lot more complex. Do you see what I'm trying to say? I think I can see what you're saying, but I think in practice it would have made describing what happens and actually implementing it kind of complicated. Yeah. So this way around, yes, you have to figure out where you're at in the level, but every time you have a team of threads, we can rely on the fact that the numbers are going from 0 through maximum number 1.
In one way of saying, it's putting the burden back on the programmer. It's
true. It's really true. Yeah. Yeah, I guess another way of saying this is too that some of these things kind of came after the start. So so we had this world with the team of threads before this was worked out. So and before people I think realized what they needed to make it more powerful. But your point, I mean, it could have gone either way, but that was it was the easiest way to do it. Yeah. Yep.
So if I deal with nested parallel regions, is there any restriction on using the thread private?
Okay, so the thread private as one word?
Yeah, yes. Like one word.
You wouldn't really use
if I'm
that,
actually
right?
in a nested one, can I get out and, like, if I have several levels, can I get out and then suddenly start to use it?
I don't think you can do that with nested, right? I never tried to do that. So let me come back and have a look and see what it says about that. But the thing with thread private is that you have to have, you can't do that, no. I couldn't see how that could ever work because you have to have consistently the same number of threads. Yeah. Yeah, but they're new ones. So I know. Yeah. Yeah.
Yeah, actually my comment was,
yeah.
I still don't quite get it. Why is it possible to have a different number of threads? And then actually when as you gave the example, you had initially only 60 something, and then or whatever the number, anyways, you have more. Mm-hmm. Why not to actually initialize those with, in the same way that the initial threads were initialized? Like, yes, you might have, mm-hmm. you might bring the data, but the rest would just be like a default constructor.
I'm not sure. I'm not think I'm getting the question. Can you kind of say that again?
You said that you can start, if you use the thread private, you can start with different number of threads that you had before, right?
It has to be the same number.
Right.
Mm-hmm.
So the reason is because you don't have data for part of them.
Mm-hmm.
But how initially when you start with the parallel regions, you also didn't have the data initialized, or you initialized in a certain way, so you could actually get the data from some of the threads, and the rest be with the data as if it were initialized for the first time.
Yeah, but the extra thread, the thread private variable for the extra thread is undefined, right? That is just happening.
Maybe we can discuss after.
Maybe, yeah. I mean, so what's really happening when you start up that parallel region is that memory regions are being set up for each of those threads, right? And if you've created for, let's say, 8 threads, you've got those 8 memory regions, and they're kind of hardwired in. But we can, perhaps we should talk about it offline and just sort of see. And it was that there was a lot of these things are, you do what seems to be the best thing. It's not that you can't do something else. It's just either too tricky or too complicated or too hard to explain, or so it's not. There was a lot of discussion about thread private and actually whether it could be more generalized. And the question is really, do people really want that complexity? So we'll find there's only one Kelvin, right? So question is, where does he spend his time implementing to? So if something becomes arbitrarily complicated to support, then A, it could degrade performance for everybody everywhere, and B, it could prevent something else from being done that perhaps is more useful. And I guess so sometimes these things, it isn't because you can't do it at all. It's because it was deemed to perhaps not be useful enough or easy enough. Yeah.
I had a question about thread private. So I was trying to think about a good usage scenario for it. Mm-hmm. Say I have a big loop, and inside the loop I'm calling some old Fortran function, like decoding, let's say. So like an ODE solver. Mm-hmm. It's written in old style Fortran, common box all over the place. I'm not interested in making that solver parallel, okay. But I would at least like to be able to break my loop up. So is that when I go into the old package with thread private and start, specifying that the different common blocks ought to be thread private?
It could be. I mean, the big deal with thread private, I'm sorry, I thought nobody was interested in that, so I was trying to go back. I'm goofed up a bit here. The really big thing that you get with thread private is that it persists. All right. So in other words, you can do your work and you can exit the parallel region and you can start up a parallel region, and the data that you had inside that other parallel region is still there. Otherwise, you lose it, right? So if you have private data, you do your stuff and you exit the region, and that's just it's finito gone, unless you have a last private and you'll keep a value, right? So it is one way to deal with it. Certainly, its rationale for existence was to help people who had common blocks and to try and let them try and I won't say minimize, but reduce the pain of trying to reuse that data. So I think you're on the right track, is what I'm saying. Yeah. So okay, well, I'm glad someone cares about it. So. But yeah, so it was one of the features that led to a lot of discussion on what could and couldn't be done, and what should and shouldn't be done. So it's because it is tricky to support it in memory. Okay, so nesting again was, I won't say it was an afterthought, but it wasn't very well thought through in the early versions. And so having these additional routines in particular allows you to figure out where you are inside this level. The other thing, doesn't really say it here, you can set different defaults for the different levels. So you don't have to have, I think I already said before, you don't have to have the same number of threads executing in the inner teams. Even though that picture suggested it, they could be different. And you could have set other defaults as well. So they can actually behave differently. You not stuck with one set. There's one other thing that's really important, and I'll try to do this and then get through and say a little bit about tasking before we wrap up the morning. And that is, it's actually another kind of synchronization construct, but I deferred it to now because it's using library routines instead of directives, and that's locking. So I don't know, I hope that some of you will have used locks in other contexts and be familiar with these already. But locking routines basically will allow you to do the same thing as with a critical region. They will basically ensure mutual exclusivity. So while a thread has a lock, or you talk about acquiring a lock, right? So you probably know this from other contexts. So it has a lock, it can execute a code. Nobody else can until it's released its lock. There's a little bit of additional power with locking because you can not only acquire the locks, so setting a lock, you can also test them. So if in particular, if you say, you can identify with a thread right now, so I'm a thread, I want to, I've reached this position in the code where I want to do some work that's protected by a lock. If the lock is held by somebody else, I can go away and do some other work potentially while I'm waiting for it to be freed. So there's a little bit of extra power here and possibly fewer overheads. So those are the reasons why you might want to do this. However, what you lose a little bit is perhaps, let me put it this way, locks are a little bit more error prone because with critical regions you have the structured nature of your code, and when you're using locks you're a little bit on your own. So there's a slightly bigger risk of creating bugs. Okay, so same kind of thing though as before in a parallel region, and I've just got two threads here. One of them has acquired the lock using the locking routines. I kind of jumped over this in the previous slide, but you have specific lock variables. They're not variables in your user code, they're just for locking. And it will try to acquire the lock. Looks like here it's done that. It's executing this code that's protected by the lock. When it's done, it will release it. So it's another runtime call. And the other thread gets to the same point, tests for the lock, can't get it because thread 0 is busy in that region. So potentially, at least, it can do something else while it's waiting, and will presumably periodically test to see whether it has access. So here it looks like it's done that twice. Then it finally gets its chance and does the work. So again, if that's, sometimes that helps. Sometimes it makes the code a little bit more efficient. But it's at the price of being at a somewhat lower level. So here we have this special lock variable that we're going to use, and we've declared that we're using the lock here. We're testing the lock, and see there's this thing. So while we're testing it, If we don't acquire it, go and do some other work. When we do acquire it, we jump out and here's the green stuff as the protected work. Okay? So if you've seen this in another context, it will probably look pretty familiar to you. And I think that they're so common that I'll just skip that one, that you can see that. Okay, so the runtime library routines, I've kind of gotten to the end of what's in the runtime library now. They're basically allowing you to test for some features, test and find out what your defaults are, find out what number of threads you have, what your thread ID is, what the maximum number of processes are. So it's querying the environment, querying what you've got, setting schedules, and again, there's this bunch of stuff that can allow you to navigate your way through through nested parallelism, if I can use those words. So figure out where you are in a nesting construct. And last but not least, it gives you some locks. All right, so locking, probably should have said a little bit more about that. In interest of time, try to not say too much more. One of the very common places for using locking is with hashing. So if you have hash tables, for example, where different threads are accessing things, perhaps not conflicting too much, locking is quite widely used. So there are some very typical places where they're common. So the other piece of this, and it actually was in a couple slides and I didn't say very much about it, there are a bunch of environment variables that you can set. All right? So you can determine some of the execution environment through these variables, but you can override them. So if you have, for example, if you set the number of threads as an environment variable before you start your program, you can use the runtime routine to actually set a different value, or you can set it as a clause. So you can override these things, but if you know what you want from the start and it's clear, then you can set them in the environment. If you don't do that, the implementation will make some decisions for you. And so for example here, the default schedule for IBM is auto or automatic, which means that the implementation is going to say reserve the right, I guess you could say, to do its best for you. It will choose whatever schedule it thinks is best for you if you don't say what it is. That could have been static, right? For some it's static. Something else that's interesting, dynamic here is set to false. So as I said before, there are some environments that set dynamic adjustment to true by default. That's a very good indicator that it's expected to be used in a general purpose setting rather than HPC. That's one of the things that tends to distinguish general purpose programming from HPC, where you really want that extra control. So I'll skip over these. Again, I guess nested is false by default, so if you have nested parallelism in your program, you have to actively set that. Either set that on the environment level or set that using the runtime call. Okay, thread limit 64. Okay, so that's the maximum number of threads that you can use. There are just two things I wanted to say at this point before we totally leave this part and I spend the last 15 minutes on threads, which is what I have. There are quite a few places where, in an OpenMP program, where threads are potentially waiting for other threads. Okay, so when threads are waiting, there's two ways they can be doing that. They can be spinning. Remember, think of spin locks and things in the past. So locking is one place where they may be waiting and repeatedly testing for something. So they may be actively busy waiting, trying to figure out whether they can proceed all the time, querying something, or they can be sleeping, essentially, and be woken up when something happens. So when something's busy waiting, it's much faster to respond. All right, it knows very quickly when it can gets a lock, for example. However, it's consuming resources while it does it, and the more resources are shared, the more potentially expensive that becomes in terms of degrading other threads. So when something's asleep, it's not going to upset other threads too much, but it'll take a bit more time to wake it up. So question is, should implementations actually be busy waiting, or should they be sleeping? Most implementations, when you do nothing, actually have some kind of a combination of those things. So they'll probably busy wait for a little bit and then sleep. However, we had a lot of discussions in the OpenMP context, given the potential impact on performance, because this can happen in lots of places, is, should the user be able to influence this? And if so, how much? And the decision we came to as a community in the end was that, yes, you should be able to say something, but we don't want people to have to say too much because it becomes very intrusive. So, so we have a way, it's an environment variable that can allow you to say whether you would prefer the system to be active or to be passive. Active means busy waiting, passive, go to sleep. So you can ask it to prefer one over the other. Most of the time, I think if you say nothing, you will get a combination that's probably reasonable anyway. I'm just guessing, but you can actually say something about it. So if you think, for example, that there's not much contention, or it's really important to have the threads being responsive, you could, for example, choose active. The other thing I glossed over a few times was the stack. And one of the reasons is whenever I tried to say more about the, I'm sorry, yes?
One question about the wait policy. Can you change it on runtime on different parts of the code?
Sorry?
Can you change the wait policy on runtime?
I don't think so. Yeah, that's something to do that, yes. Yeah. Yep. Okay, so the stack, so we used to say a bit more about the implementation, but I think most people found that very boring. So, so stack is a place, I guess, where you park the data that's local. So not shared data, but things that a thread needs. So each thread has its own stack, and it's a region of memory where its private data is stored, and usually a bunch of other stuff, for example, register variables and so on. And so one of the things that I find this very distressing, actually, because I think it's the sort of thing that users should not have to see. But unfortunately, what happens in this context, because you have a whole bunch of threads, is that the implementation goes and reserves specific memory spaces for these. And the question is, how big should that be? And nasty things happen if it's too small. So sometimes you as a user have to actually set a stack size. And again, like I said, I don't really like that, but it's a fact of life. So there is a default stack size. Your program can run out of it. It may need a lot more stack than you think it should need based on the data that you have, because it may be saving a lot of stuff that's related to the registers and sort of what's going on at runtime. So that's there too. And if you get an error related to your stack size, you have to go and raise it and play with that and try and get it. So yeah. Okay, tasking, and I'm out of time, so I've got to really rush. Okay, all right. So. Tasking is something that became part of OpenMP in version 3, and it was quite a big step. It was a big change from previous APIs in this whole area. There was research, for example, Silk, if anybody has used Silk here, had a kind of tasking. So there were groups, there were APIs that had provided tasking as a fairly basic construct for parallel programming. But marrying that together with the features we had was quite a challenging task, actually. So we had this thread-centric model, and now I want to provide tasks. And the rationale for it, I'll say just a little bit about what it is in a moment, was to enable parallelization of a whole bunch of things that were either borderline impossible or at least very difficult before that. And I tried to hint at that one time earlier by showing a piece of code where there was a while loop actually traversing a list and saying, well, you can't turn that into a parallel loop using a for or do, because it needs to know what its iteration space is. And this one, you're following a list, you don't have that information. So there are a lot of codes out there that do that, and how can we make them, how can we allow people to parallelize those two without lots of rewriting was the challenge. And this is still undergoing evolution. So the notion of tasks started out, and it's what I'll show you now, as being very simple, and it's growing in functionality and becoming more and more powerful, which I think is actually quite exciting. So typically, tasking in OpenMP, we expect a thread to be busy working creating some tasks. And conceptually, those tasks are going somewhere. We talk about this pool of threads, right? So those tasks are being created, and at some point, they will be executed, right? So deliberately nice and vague. And while threads are being executed, some new ones could also be being created. So the thing about tasks is it's a piece of code and associated data that's going to be generated, or created if you like, and it will be executed at some point. But the creation and the execution are divorced from each other. And in the initial OpenMP, again, you'll see some updates this afternoon. Initial OpenMP, these are all completely independent tasks or independent pieces of work because they were going into this thread pool and they would be executed somewhere by some thread, but you didn't know exactly when, so you didn't know what order either. So they had to be completely independent pieces of work. So a bunch of pieces of work, and they will be pulled out and executed by one of the threads in that team of threads. Okay, so specifying them is pretty easy. So just a task, all right? It's a piece of code, and it has some data associated with it. So you can think of it as the data is being captured. When a thread actually hits this OMP task, it will generate the task, all right? And the task will go into this pool. Like a lot of other things, OpenMP is deliberately a little bit vague about how they're executed to allow people to do the best for their own environment. So generate it, and there will be some data associated with it. And okay, and I think it's saying the same things. So this assumes that the tasks are all independent, so they're all going into this task pool. They will be executed in some order, but we don't know which, so we shouldn't assume anything. Okay, yes, in fact, they can even be nested. And it will be executed by one of the threads in a team. I'll say something about that in a moment. Possibly right away, but possibly not, right? Possibly it will be waiting in that pool for a thread to be ready to do that, and so on. So when you have this team of threads and you say, well, they can be executed sometime, well, you do not want to have some guarantees about when that happens, right? So there has to be some synchronization there too, and it turns out, so if you have a barrier anywhere, then by the time you leave that barrier, as guaranteed that all of the all of the tasks that were created before that in that team will have completed. All right, so in other words, if you had a parallel construct where they're all being created, when you exit that construct, they will all have completed. All right, so have that, you won't know exactly what order, but they will have happened. And there is a new construct that enforces completion of tasks too. So there's a little bit of extra help here. Okay, all right, so here's a piece of code. It's all right. So with a couple of tasks in it, I'll just jump over this. So we got a task with some shared data, another task being created, and now we've got a task wait. And at that task wait, we won't leave that task wait until those two tasks have completed. All right. Doesn't say anything about any other tasks, but those two tasks have to guarantee to be done. All right. So task wait enforces that extra piece of synchronization on the tasks. Okay, all right, so this is perhaps a little silly, but here's just a quick example of something, the possible consequences, very, very simple. Very typical though, we've got a parallel region and we've got a single loop which is creating tasks. So one of the common ways in which this would happen would be to have one thread generating a bunch of tasks. Okay, so in the single, it's printing something. This is apologize for the silliness of this a little bit, but okay, it's creating a task that's going to print out race, and it's another one that's going to print out car, and it's also then printing out as fun to watch. And one thing that could happen there is the is going to come first because that came before the tasks, so there's a applied synchronization there. And then there's this fun to watch, and then sometimes we get car first and sometimes to get race first. So that's what happened here. If we really wanted to create a coherent sentence, though, we'd like to be sure that the car and race actually come first, either a race car or a car race. So to do that, this task wait can be introduced, and that way we can be sure that that these tasks are completed before this print. All right? So otherwise, if we don't introduce that task wait, we don't know. All right, so the guarantee that without the task wait, the guarantee is that they'll have been done by here, but there's no guarantee that will happen before this print. Okay, so introducing that task wait will enforce the ordering, and we get something like this. And because there's a randomness, if you like, in terms of the two tasks in this case, we don't know which one will be done first. So you might sometimes get a car race is fun to watch, and other times you might get a race car. Okay? So there's this sort of element of minor randomness. Okay, so a few other things just to wrap up on. One of the things that can happen if you're creating tasks, especially if you're doing it recursively, is that you might end up with some very small tasks. So we like to have a cutoff point, and that really means is going to say that, well, there are two things here. First of all, if some value is small, you might want to execute something immediately. So the other thing I was trying to talk about here, as jumping, was that you might want to say that I don't want to execute any more tasks at all. This is the last one, this is the final task. And sorry, this kind of messy kind of notation here, but you say this is the last task, I'm not going to execute anymore. So particularly if values get smaller and smaller, you don't want to keep on creating more and more little tasks. Okay, just two things I want to say. So I'm looking at the watch here, and I'm sort of out of time. So I jumped over the data scoping with tasks. So there's not a lot that you have to worry about here. Remember, when task is generated, it also has a data environment with it. It's still in the same parallel region, right? So if data is shared in that parallel region, the task is a piece of code in that region executed by a thread in that region, so it can still execute the same shared data. Right, so that doesn't change, fortunately. Private variables, there's an interesting thing. So because of the separation between the time when the task is generated and the time it is executed, we actually have a default of first private. First private means that actually it's going to take the value that it has at that time and capture that value. So look at the example here. Okay, so just inside this, we've got here's a parallel region with parallel and, A is outside of it, B is private, and here's our task. So A is shared data, all right, it's shared in the parallel region, no change. All right, here's the change. B is private variable, so it means each thread has its own copy. When the task is created, this becomes first private. What that means is it's private, but it's going to get the value from the thread that created it. Okay? So if you like, it's got that specific value. So it's got this C it's shared data, so D again is private, so it's going to become first private. So it's going to capture a few values, right? Shared data, a lot of the time we have shared data, there's no change whatsoever. Okay. One other thing I wanted to say, and then I really am out of time, and that's called task scheduling. So I won't go through all the details. Some of this is actually a bit of a cut and paste from the spec, so it's not very exciting anyway. One of the concerns when you're generating tasks, so there are plenty of times when, obviously there are other scenarios, but there are plenty of times when you'll have a piece of code that looks a little bit like the one you saw here, where you have a single, so you have just one thread is generating a bunch of tasks. So there was a very real concern that your system might create too many different tasks and basically flood the system, right? So if you have think of one thread here and it's busy creating tasks, and after it's created a trillion of them, things start to get, kind of nasty. So well, you have to somehow be able to suspend that and do some work, so you have to have some point where you sort of say, in particular, I'm not going to generate any more tasks till I've processed a lot of the ones that are waiting in this pool to be executed. And so we have some places where that we call task scheduling points, where the system is allowed to suspend a task and resume it. And if you really care about those, you can go and look for them. You can actually also, so in the bottom, you can actually set some of those points. So you can give a hint to the system, if you like, that this would be a good place for it to not do that. Okay, the other thing that's really important, well, actually, I don't know how really important it is. I think it's probably not, but it's important that I mention it, is that tasks can actually be tied or untied. And I think we pretty much use tied tasks. At least I certainly would want to do that. A tied task actually means the following. If, let's say you start running a task, all right? So executing it on a thread. So thread's picked it up, it's grabbed it from this pool, is executing the task, and it's hits a scheduling point, and it's basically, sent away, put to rest for a little bit while that thread does something else. That's what it's allowed to do. Question really is, does the same task execute it again or not? Most of the time, you probably want the same task to do it again. All right. So in other words, if thread 0 has been executing a task, that task is suspended. When it comes back again, if it's a tied task, it's guaranteed to be thread 0 that completes it as well. Nobody else can. If it's an untied task, right, then thread 0 could start out doing it, go off and do something else, and thread 33 could pick it up and finish it off. If you have an untied task, you need to be a bit careful about things, because if you're using data that's been private to a particular thread, then you could be in trouble. So for example, the thread ID would suddenly change under your feet, right? So most of the time I think, assume threads that tasks are tied, and it's certainly the default, but it is possible to declare them to be untied. So just so that I haven't forgotten. Okay, and a quick example. I'm over time, so I will just stick with this example and just make sure we've seen it. So again, this is a very, very common scenario, and this was one of the motivating reasons for having this was wanting to be able to parallelize loops that traversed a list or some kind of a structure. And with OpenMP tasking, you can do this by having, again, this not the only scenario, but a common one where you've got the single clause where the thread that executes the single is going to start generating all these tasks. And in each of these tasks, they're going to be doing this work. And the tasks, again, are all being generated by this one, but they can be executed by all the different threads in the team. And here you don't know which thread is going to execute a piece of work, and you don't know when it's going to happen, so it's very important that they're independent pieces of work. Okay. So a couple of things, if you're looking, I said this at the start, but I'll say it again. If you're looking for more tutorials, more information, the OpenMP website's a good place to go. You are always very free to download the spec and actually specifically look at all the details. It's gotten, I find it much, much harder to read than it used to be. It's just size. I don't know if you call this success or another, but it has over 300 pages now, and it's much, much harder to read than it used to be in terms of rules. It's written for language lawyers nowadays, but on the other hand, if you know what feature you have and you want to see what particular rules apply to it or want to check up on something, I do think that is still quite readable. So it's all there. There's a book that I wrote with a couple of colleagues some time ago now, which actually goes up to OpenMP 2.5, and I have a copy here if anyone wants to look at it. The examples from that book are actually all online, and you can download them and use them as well. So I assume you better see this slide from the agenda, so you can have a look at this if you'd like to. But certainly those are things there that you can try out just to get examples of things as well. Okay, so this morning what my goal was to go through the basic features, and I hope, with perhaps one exception, we got there. Well, one slight miss. It's all in all has quite a lot of power, especially if you compare it with previous attempts to provide shared memory parallelism. So it has quite a few different ways in which, or say, offers quite a few different ways in which you can create parallel code. So you can either do that in a fairly manual style by using library routines more or less exclusively, or you can do a lot of things at the high level. The most important thing to me about it is that it's portable, and that the vendors have sort of worked together and synchronization, sorry, it's a bit of a pun, to provide some non-trivial features and to do a good job of the implementation. OpenMP, as you experience it, is very dependent on the quality of the implementation. So there are some things, especially in very early versions, that, well, were real slow and that have gotten better and better over time. So something that's compiled has this effect. So the amount of effort that went into it really shows. And sometimes things that didn't work very well in one release are much better in the next release. So don't give up on things if they're not immediately great, especially with new stuff. What we're going to do in the afternoon, other than is first of all be looking at how to use OpenMP together with MPI and some examples, but also we're going to have a portion on OpenMP 4. So everything I've talked about now is OpenMP 1 through 3. And OpenMP 4 is a very big departure from previous versions of OpenMP. And if we'd had our way, we would have actually given you OpenMP 4 to use in the exercises, because we think that there are a lot of features in it that are very important for HPC. Unfortunately, we're not quite there yet, so I hope when this event takes place next year that people there will be luckier and they'll have the full power of OpenMP 4 to use, because I think there's some very, very important changes or extensions, not changes to existing stuff. And so since we do hope that will be available in the near future, we want you to see them and know that will be coming and get some idea of what they're like.